Yeah, g'day, it's Charlie ZL2CTM. Well, I just wanted to spend today with a quick video to have a quick chat about the crystal filter. You may recall I mentioned that I had purchased 2 lots of 100 crystals for the princely sum of $6.41 each. It's a bag of 100, that is. One at 4.9152 megahertz and the other one at 9 megahertz. And the aim was to build 2 crystal filters, one for CW and one for SSB. And the approach I was going to take was to build a very simple ladder filter or a Cohn filter where all of the capacitors are the same value here. Before I got into actually soldering the capacitors, say again the crystals into the filter, the approach I took to characterize the crystals was to do it by frequency. It's not the textbook approach for doing crystal filters. It's a very simple approach. It's an approach that certainly worked for me in the past, so I was quite keen to give it a go again. So in order to do that, I needed to look at each of those 100 crystals. I started with the 4.95 ones, and to measure their frequency and then basically set them aside, and I put them into little bins of 5 Hertz. The way I did that was to use an approach which I've used before, which has certainly worked well, which I'll look at in a sec, and that's to use a simple communications receiver to receive not only the crystal filter and it's what RF it's radiating, but also at exactly the same time the output of a signal generator on the same frequency. And if I get the SIG-gen to be on exactly the same frequency as the crystal oscillator, I get a single tone coming out of the radio. When I get slightly off frequency, I start to get a beat frequency. And the approach is to basically adjust the signal generator till I get a 0 beat, and then I can read directly off the SIG-gen, because this goes down to 1 Hertz, what the frequency is for that crystal. Now, this is only a relative approach. This is not a high-end, for example, laboratory SIG-gen that's being calibrated. So, you know, but that's fine, because at the moment in this room, and when I did the actual characterizations by frequency, I made sure that there was no temperature variations in the room. Everything was all nicely warmed up to try and take away any variables. All I was after was trying to get a bunch of crystals that were all roughly at the same frequency. If they were all slightly off by the same amount because of any inaccuracies in the system, that doesn't matter. As long as they were all off by the same amount, it worked for me. So that's the approach I took. The actual crystal oscillator is very straightforward. Again, just a 3904. Fixed voltage biasing here off the 13.8 volts of 100 k ohms. In the emitter, I just throw a 1 k ohm there with a small fly lead that you can see there. You don't actually need it. There's enough RF being emanated or being radiated, more the point, for the radio. And then on the input side, just the split capacitors with the crystal under test across that, driving the overall frequency, and that works really well. So what I'll do is I'll just turn on the radio now, and it's probably going to be a bit loud, but you'll hear basically no beat, and then I'm just going to tune off the SIG-gen both above and below the crystal frequency, and you'll hear what I'm talking about. I normally do this with headphones on, and it's really clear in your head, and you can tune it up very quickly. I was getting down to around 1 every 20 seconds in terms of putting it in, let the temperature stabilize a bit, because you don't want to have too much heat on this, because that also varies the temperature, so again the frequency. But like I say, it worked out well. So that there is a single tone that's picking up both the SIG-gen and the crystal oscillator. Now if I was just to tune slightly off, you'll hear that beat coming in. That's slightly high in frequency, coming back down again, back down to 0 beat, and then going below the frequency. And the further I go, the higher the beat. And I'll call that good. And then I just read off the last 3 digits, and that's how I had the divide up. it's only ever the last 3 digits that vary enough. So in this particular case it was 4914, and I'm interested in the 877. And that's the approach I took. So I did all 100 100 crystals using the same approach. Had them all bunched up. I did that for both the 4.914 and the 9 megahertz. And what was really interesting was the spread in frequencies. The lower frequency ones, the 4.914, had a really nice, poorly drawn here, Gaussian distribution there around the actual, I guess, spec frequency. Very, very nice, and had a big bunch in the middle, and then not so many on the skirts, both below and above the frequency. Interesting enough, the 9 megahertz one, not drawn like this, but just trying to demonstrate that the frequencies were all over the place. I had some that didn't even work. I had some that I put them in there, and I could tell straight away that the crystal burst into a harmonic. They really were a mess, which really makes me think that they had failed some kind of a quality control check on a production line, and were literally scooped up by the handful off the floor, dumped into a plastic bag, and then hocked off for cheap. So they really weren't too flash at all. So coming back to the 4.9 megahertz one, I then looked at making a Cohn filter, where I elected to go with 6 crystals that were within 50 hertz, and in each case I actually had them within 10 hertz. I had 2 bins of 5 gigahertz bins side by side, and there was tons of them in there, so they were very close. As it turned out, I had quite an acceptable CW filter, but I really could not get the SSB one to have the kind of pass band that I was after. It just really had too much ripple. No amount of adjusting the terminating impedances, or in this case resistance, if I ignore the reactance components, would fix it. So potentially, if I'd gone through a more rigorous approach and actually worked out for each crystal the inductance and the capacitance and the resistance for the crystals, and then put them into a proper design program, then chances are I may have come out with a better result. But for the approach I wanted to take, like I say, I just couldn't make the SSB one work. So what I elected to do, I already had some 9 megahertz ones that I had purchased some time ago. So I pulled those out, and they had also been characterized by frequency using the same approach I just showed before. So I grabbed 2 lots of 6 and made up a CW and an SSB. The way it worked out in the end, the SSB filter there, all of the capacitors, like I mentioned before. The particular configuration for this is all the crystals are in series, any number, and then in parallel we have capacitors of all the same value, plus 2 terminating, or an input and an output capacitor, which is also of the same value. For the CW, I had a nice, which we'll show in a sec, pass band of 2.9 kilohertz, which is what I like. I prefer to have a slightly wider bandwidth than, say, 2.4. Which is great, and that was using a 75 picofarad capacitors. And then for the CW, for this type of filter, the higher in capacitance you go, the narrower the bandwidth, and that was got down to 330 picofarads. Insertion loss for the CW, slightly higher with the bandwidth, so minus 11, so not ideal, but hey, I'll give it a go. And the SSB was minus 6 dB. So I'll live with that. The other interesting thing was I tried to use my Nano VNA to look at the pass band, and in the past I've certainly had good results using this, certainly with the likes of LC low pass and band pass filters, but for whatever reason I really didn't get a good result at all using this on the crystal filter. So if I was just to, let me just plug this back in again, and then I'll come back to what I ended up having to do. Plug that into there, let's just plug that into there. So we're currently looking at the CW filter, and as you can see it's really spiky and horrible, and it's not anywhere at all in line with what I'm getting on the spectrum analyzer using the tracking generator. And if I was just to quickly move across to the SSB filter, we get a similar response. It's just not really what I'm after, and a bit hard to try and design to. So sorry about the reflections there. Yeah, a little bit disappointing, so I'm not quite sure why that is the case. Yeah, I'm at a bit of a loss at why that is, because like I say, I thought I'd had good success using these with crystal filters in the past. So what I had to resort to in the end was using the, like I say, the spectrum analyzer with the tracking generator. Let me just take that off. Let me just plug that back into here, and plug that back into there. And let me just move the camera up. So what we're looking at here is the spectrum analyzer, like I say, with the tracking generator, just tracking across the frequencies there. Let me just get rid of that marker. So and as you'll see, that's the SSB one there, and quite different from what I'm seeing on the Nano VNA. Not a perfect response, but hey, I'm happy to give that a go. Got a little bit of a dip down there in the at one of the extremes, but like I say, I'm quite happy to give that a go. To the ripple itself is not too bad. It's only just under a dB of ripple there, and that's using a termination resistance of all up 170 ohms. So that's 50 ohms from the SIGGEN plus 120 ohms for those two resistors. And as you'll see later on, once I know now that I know that, I can then work out what the turns ratio needs to be for the two IF amplifiers. If I was now just to move across to the CW filter, let me just change that to there and change that to there. So this is the CW. This has a bandwidth of 560 hertz, so I think that's quite good. I don't really want to go a lot lower than that, so I think that's quite fine. So I will give that one a go, and if we can get our CW signal to be in there, then we're looking pretty good. So yeah, happy with that. So yeah, I think that's all. Let me just come back down to here again. Let's get my thoughts. We talked about the Nano VNA, and like I say, next steps now is to turn my attention to the IF amplifiers. I took the opportunity the other day just to quickly make up the base part of that, which is the transistor and the DC biasing. And what I need to add to this now is the collector load. Being an RF, it's going to be a transformer, and then so there'll be a transformer on the input and a transformer on the output, because this naturally now sits on either side of the crystal filter. So the actual transformers themselves will have to reside on the crystal side, because as I said before, this particular the CW filter wants to see 50 ohms, and the SSB filter wants to see 170 ohms. So like I say, I'll have the transformers on the crystal side. What I do need to then work out, and I'll cover that in another video, is working out what the output resistance is. I'll say impedance, but I'll ignore the reactance components of the IF amplifier, and I'll just use that using measuring the output voltage for a known input open circuit, and then I'll put a load on it for the same input, and I'll vary that load until the voltage then drops to half the open voltage. I'll then measure that resistance, and I can say then that's what the output resistance is. Once I know that, I can then start to work out what the turns ratio needs to be to match that resistance to what the two crystal filters needs to see. And the same approach on the input. I'll mathematically work out what the input resistances of the stage, and what I may even look to do is actually compare the mathematical calculations with a test calculation using, say, the nano VNA. We'll see how close that is. Anyway, so that's going to be the next stage. So I think I've rambled on long enough there, so I will say 73. And like I say, this is not for everybody, this approach. It's a very simple approach with these crystal filters, but like I say, for me, they have worked in the past. And I do need to acknowledge that in this particular case with the 4.9152 small profile crystals, which others have used very successfully in crystal filters, I couldn't get it to work without a simple approach. And like I say before, that may be a candidate now for a more rigorous approach. But I'll say that for a different project. Okay, 73. Take care, everybody, and I will see you next time. Cheers all.